Hello students, in this little video I will go over how to use some of the functions in the first computer assignment, which is two sample t-tests. So we have two groups of data, group A, group B. There's some values hidden here. We can unhide those. So in your computer assignment you're going to have something similar to that. The interior values will be hidden, just so we can still have space on the screen to work on things. So what I want to do, I'm going to show you some Excel functions. The count, the average. The count is going to be your sample size, the average, and then the standard deviation functions. The count function equals count. Highlight all of your data in column B for group A. Average. To calculate the mean, go equals average, bracket, highlight all of our data. And for our standard deviation, STDEV, bracket, highlight all of your data. So that's the count, average, and standard deviation. We're going to copy it over there. So count, or group B, has a different sample size. What we can do as well might be easier. You don't have to do this, but the variance is going to be just, squaring the standard deviation. There's a variance function we could use as well. It's just VAR, bracket, highlight the data. So I just want to color code that data there. So this is our data, some of our characteristics. So one of the things we want to calculate here is our degrees of freedom. I'll just abbreviate that DF. Degrees of freedom in two sample t-tests is the sample sizes minus 2, n1 minus 1 plus n2 minus 2, or minus 1. So our degrees of freedom is 126. We then need, in order to go through this, we need the pooled variance. Oops, let's put that over there. Pooled variance estimate. This is a formula that you have in your formula book. It's the variance of group A times sample size minus 1 plus doing the same thing for group B. The variance times sample size minus 1. Close our brackets. So what we need to put in here, and I forgot to do that, is brackets around everything, beginning to end. And then we can divide by the degrees of freedom, or we can divide by n1 plus n2 minus 2, which is our degrees of freedom, 126. That's our pooled estimate for our variance. We need that in order to calculate the standard error. The standard error formula is the square root of the pooled variance times, in brackets, 1 over the sample size plus 1 over the other sample size. Oops. Let's just make sure I got that formula right. And we need to double close our brackets at the end. So it's the formula you have, it's a square root of the pooled estimate variance times 1 over the sample size for group A plus 1 over the sample size for group B. Our standard error would equal that value. And now we can finally calculate our test statistic, which is going to be the difference between the averages, in brackets, divided by that standard error. So there's our test statistic. Doesn't matter if it's negative. It's only negative because we went the lower average minus the larger average. We could have reversed that as well. Critical value. Let's put that in there. Critical value is going to be using an Excel function. It's for key INV. Probability, that's the level of significance, alpha, 5%, and degrees of freedom is n1 plus n2 minus 2, or 126 in this case. There is our critical value. This is the critical value for a two-tailed hypothesis test. We're going to calculate for the one-tailed hypothesis test as well. This, in order to find it, it uses the similar function t inv, but it's t dot inv, t dot inv, and then we enter everything the same. 0.05 is our level of significance, and 126 degrees of freedom. The one-tailed will always return a negative value, so at the very beginning of your function, put a negative in there. Then there is our critical value for our test, our critical value for this two-sample t-test. So our decision is always to reject the null hypotheses if our test statistic is greater than our critical value. So once again, ignore the negative signs. So based on our values here, I'm just going to put this on here. A decision based on whether it's a two-tailed or one-tailed test. Our test statistic, 3.41, is greater than our critical value for a two-tailed test. So we're going to reject the null hypotheses. And we're going to make the same decision for if it was a one-tailed test, reject the null hypotheses. Because 3.4, let's just color code that because that's a key value, 3.4159 is greater than both the critical values for the two-tailed and one-tailed test, so we reject. We can calculate a p-value as well for both a two-tailed and a one-tailed test. This function uses the t-dist function. Bracket x is our test statistic. This has to be returned as a positive value. So I'm going to put in the ABS function in there. T-dist. If your test statistic was positive, you wouldn't need that ABS function in there. We could have just typed in there T-dist bracket 3.41596. Degrees of freedom, we have that calculated, and we want a p-value for a two-tailed test. There's a p-value. Our decision rule, once again for a p-value approach, is to reject the null hypotheses if the p-value is less than alpha. P-value is really small. It's less than alpha. We will make the same decision to reject the null hypotheses. P-value for a one-tailed test, t-dist. I'm just going to manually type in. It's really not always the best practice to do so, to manually type in values that we have in a spreadsheet. I'm going to do it for this case. Degrees of freedom, and comma 1 for a one-tailed test. And there's our p-value for one-tailed test. Remember, the p-value for two-tailed test is just twice that of the p-value for one-tailed test. So we are going to reject the null hypotheses based on the p-values, as well as based on the comparison between the critical value and the test statistic. So this is how you would do it if you were given these values in blue here. We would calculate, the pool variance, the standard error, the test statistic, and using Excel to find the critical value and the p-value. We can find the critical value on the t-distribution chart if that t-distribution chart has or if the degrees of freedom is on that t-distribution chart. And I can just bring that up quickly here. Let's just do that really quick. T-distribution chart. So for a one-tailed test, alpha is 5%. So we'll be looking at this column here, the 0.025 for the two-tail test, I should say, and we'd have to go down to 126 degrees of freedom, which we don't have. But if we did, if the t degrees of freedom is on this chart, we can use this chart to find the critical value. Based on 120 degrees of freedom, our critical value is 1.98. We have a critical value that's very close to that with slightly more degrees of freedom. Now, when our data is presented, if our question has data that's the whole data, the raw data, another process that we can do is under the data tab, data analysis, the two sample assuming equal variances. That's the analysis tool that we can use. You click on that. Basically, value A, or variable 1 range, is going to be the label plus our values. Same thing here. We're going to check mark labels, and the hypotheses mean difference is 0. We're assuming that the averages are the same for a two-tailed test. And output range, I'm just going to on this page somewhere, let's put it down right there. And this summarizes everything that we've done already. There's the averages, same averages we have we've previously calculated. Let's just color code that as well. The variances, we have the same variances as we did before. The observations, which is the count, and the degrees of freedom, which we have. The pooled variance estimate, which is what we have right there. It doesn't give us the standard error, but it's part of this test statistic calculation, which is the same value we have there, and our critical values for one-tailed and two-tailed tests with the p-values are the same p-values we have here. So using the analysis tool can be done when we have the raw data. If you don't have the raw data, then we have to calculate these. We don't have the raw data, then we're given the count, average, and standard deviation. We're given these values, and then we have to calculate the key values we need to make our decision. If you have the raw data, you can do it either way. You can do using the analysis tool, or you can do the process that I've done here. So hopefully that will give you a heads up on how to use the functions and what functions to use.